Dear all, I think it's time to start, but you all know that last weekend we lost Professor Łukasz Turski. People know him very well, so he was co-initiator of the Center for Science, Nicolaus Copernicus Center. He was also initiator of the scientific picnic, which is gathering, well, tens of thousands of people every year. He was also very influential on higher education system in the 90s. He's meant to be one of the rescuers of some of the institutes of the Polish Academy of Sciences in 2012. He was a very known popularizer, also colleague and mentor to many of us. So that's why I propose that before we start today's colloquium, I will ask you for a moment of silence in memory of Professor Turski. So let's stand up. Okay, thank you. So after this sad news, we go to our usual things. And today also is a special day because we have a very distinguished guest, Professor Tomasz Dietl, who's also very, very known in our community, in whole Poland. As many of us, he was graduated from the Warsaw University, from the Faculty of Physics. He received a number of prizes, including the so-called Polish Nobel Prize, so the prize from the Foundation for Polish Science. He received the IRC Advanced Grant. Actually, he was a member of the steering committee of IRC. He's also very influential on research politics in Poland and also abroad. He's also meant to be one of fathers of spintronics, so the whole discipline. Some time ago, last month, we have seen reporting sessions of the Institute of Physics. And as always, there's a list of top 10 publications in terms of citations. If you remember, a big part of these publications were actually co-authored by Professor Dietl. And now he is also director of MagTop, big institute, which is for me amazing that he's a theoretician and still he can manage the institute with very nice experimental results also. So now I will give the stage to Professor Tomasz Dietl.
Thank you very much for this kind invitation and kind words. Just explanation, I did my PhD from experimental physics, so it's kind of explanation how it can go. As you see in MagTop, we are from 14 countries. It's a very international community, and we are proud that probably this internationalization, which everybody regards as important, MagTop develops, and probably you mentioned phase transition, those who are here for several years, when MagTop was created, how many international colleagues are with us. As you have seen, I would like to devote this talk to memory of Professor Łukasz Turski, great friend of many of us. It was always wonderful to interact with him. Tell you the truth, I believed that he will be present here, and I prepare everything waiting for his nasty questions. Unfortunately, he passed away, and this certainly very important and well-taken questions actually will not be asked, which from Professor Turski always can be expected. Well, what I'm always saying, if you want to explain to your mother-in-law what are semiconductors, you should say about doping. One word, critical word, is doping. It can be doping by gates, it could be doping by impurities, it could be doped by light, and in many other ways. And if you think about nowadays technology which are using semiconductors, this doping, of course, is essential. And today's message of today's talk would be, key role of charge and magnetic dopants in quantum Hall effects. This is kind of bottom line of this present talk. And in particular, I will focus on materials, mercury telluride, mercury cadmium telluride, mercury manganese telluride, chromium telluride, and I will present some of results which are obtained with my colleagues in MagTop over the last years. Well, what is mercury telluride, this hero of this talk? Mercury telluride is interesting material in the sense that from textbook in chemistry of in schools, you learn that cation gives electrons to anions. It's kind of principle of bonding. We all know that electron from sodium goes to chloride, and cations, this means cation bands are above anion bands. But mercury telluride is opposite situation. We have anion p-type states which are empty, partly, and we have cation S-type states which are below Fermi energy. And this inverted band structure is a reason that this material is not trivial topological. You can find a topological invariant, and this material, therefore, is very interesting for Hall effects I will be talking about. And second things which I mentioned is doping by magnetic impurities. And we all know that magnetic impurities contain localized spin, and the spin, by very funny quantum and many-body effects, produce strong coupling, exchange coupling with band electrons or effective mass electrons, giving rise to giant spin splitting of bands, of excitons, of shallow impurity states. And this splitting is somehow proportional to local magnetization in this place, for instance, where impurities, and to this exchange coupling, which is many-body theory necessary to understand quantitatively its magnitude. And second effect, which is known, is a very interesting Kondo effect. We know it since many decades, and we know that calculation of Kondo effects is very non-trivial because there is kind of dynamic bound state between this localized spin and Fermi sea of electrons around. This Fermi sea is attracted, in a sense, if the coupling is antiferromagnetic, and screen this localized spin and give bound states. And because of the stand is bound, we cannot use perturbation theory to calculate actually this effect. And another effect, which is very important in semiconductors also for this talk, is opposite to Kondo effect. Kondo effect screen localized spins, but bound magnetic polaron enhance local magnetization. How it works? We have localized impurity states. Around these impurities are localized spins, typically 100 of localized spin in Bohr radius of impurity. And this impurity by exchange interaction polarizes this manganese around, and this polarized manganese gives splitting of these impurity states. So this kind of interesting situation where impurity, which is normally doubly, there are two states up and down which have the same energy. Here, due to this magnetization, there is splitting of impurity states. And now we move on to main topics, which is macroscopic quantum phenomena. Well, one, or maybe first discovered, or maybe second discovered quantum phenomenon is superconductivity. We know superconductivity for 110 years more. And a very interesting thing happens if you couple two semiconductors, but thin insulating layer, you have tunneling possible if layers is thin enough, and you have standard characteristic because it's Cooper per tunnel for superconductors, but the critical field, of course, depends on thickness. If thickness is large, you can imagine the critical field will be low, and vice versa. But very interesting thing happens if we irradiate this Josephson junction by microwave radiation. What actually happens is appearance of so-called Shapiro steps. You can imagine that we have photon-assisted tunneling, and if you calculate energy necessary, just simple quantum mechanics means that voltage which you apply to this tunnel junction assume steps, such steps. If you change current, actually instead of this behavior, you have that behavior, because at this point starts this tunneling and current increase, this photon-assisted tunneling, current increases without changing voltage. So you have interesting phenomenon, which is very attractive. We think about voltage standard, because to a great accuracy of that sort, this voltage step are related to frequency of this microwave radiation, which we can measure very precisely, and to Planck constant elementary charge. So we have a nice device which we can use for measuring, for calibrating voltage sources. But we have another macroscopic quantum phenomenon, which came as a surprise. Josephson effect was first predicted and then observed. Here is opposite situation. Nobody expected that if you take a piece of material, very dirty with many impurities, defects, and so on, and you measure a ratio of voltage, whole voltage perpendicular to current, and divide by this current, the magnitude, what you get, the resistance which you get, assumes again plateaus, and over these plateaus, this is quantized with high precision and is determined by ratio again of Planck constant divided by 2 over E2 or 3 or 4 and so on. So what you see here is actually we have, which we know very well, transistors. This transistor, you have how many? You have 10 billions or more transistors in your head, in your smartphone. Yeah? And this transistor, and that time, we speak about beginning of 80s, had size of 400 micrometers. Now it is 100,000 smaller, as we know, and we have, due to that, we can put 10 billion in our smartphone. But taking the standard transistor and measuring as a function of gate voltage, changing concentration of carriers in high magnetic field at low temperature, we observe this plateau with precision 10 to minus 10 again, with various integer number or natural number 1, 2, 3, and 4. So very interesting phenomenon, and immediately people started to try to understand what is going on, why we observe such high precision of quantization. And also people who tried to do experiments and found that in addition to quantum Hall effect, we have fractional quantum Hall effect, we have quantum spin Hall effect, quantum anomalous Hall effect, fractional quantum anomalous effect, and so on. So there is a huge family of system, and understanding of this phenomenon is kind of interesting for us today. So before going to understanding, we can ask the question, what is application? We found this macroscopic effects, and what is application? The first obvious application, metrology. I already mentioned this high precision, and maybe for many of us, for years, this meteorology was kind of group of enthusiasts who were sitting in some basements and measuring something with accuracy 10 to minus 10 to minus 11, and nobody paid attention how precise they are. Nowadays, situation changed. We know that this enthusiast actually allow us to GPS. Yeah? This high precision of time measuring is can be translated to precision which we can localize ourselves. So this more than just a place for enthusiasts is very practical application. But there is a second possible application, namely people, as you know, want to see new physics, maybe new find particles which could be associated with dark matter. There is a lot of interest. And one of the ways to look for them is, of course, to construct colliders. Colliders are not very cheap. It's several tens of billion of euros to construct, but of course it's one of the way. But we all know that there is another way. It's another way, namely, probably, you know, sorry, something went wrong. Yeah, there is one way to colliders, but there is another way. Atomic physics, as you know, measure very precisely G factor of free electron, measure Lambschiff, try to measure electric dipole moments of proton. And it is believed that if you measure precisely enough, if your precision is of the order of experimental energy scale to new energy scale, you have a chance to find this new energy scale. It's kind of, you can imagine and understand how it is so. So now the question is, could solid-state physicists contribute, material scientists contribute to this kind of research? And what you see here is quantum metrology triangle, which is measuring electron, oops, pardon. Something is wrong with this. Yeah, something with some, maybe, okay. So here I should mention about quantum second and relativistic meter, which everybody knows that we use relativistic effects to measure transition hyperfine splitting of 6s electron level. It's a standard of second, and standard of meter is due to the fact that we assume constant value of light. And we use also, of course, this Josephson junction and this Hall effect. Nowadays, it's a standard, which is, we assume constant value of Planck constant and constant value of charge. And due to that, we have now ampere and kilogram, which is defined not by what we have been taught in school, that it is kilogram which sit in Sèvres near Paris, but now we can express kilogram through the second meter, volt and ampere, and we have this macroscopic quantum phenomena which allow us to define this ampere and kilogram units. And what is important in this context, it's important that ideally we would like to have ampere standard, for instance. We would like to have weak magnetic fields, because Josephson effect works with weak magnetic field, whereas quantum Hall effect works in high magnetic field, standard quantum Hall effect. So we want to work how to get quantum Hall effect in low magnetic fields to integrate with Josephson junction. Yeah, because nowadays the standards work in 10 Tesla. And another very interesting effect which allows us to determine electron charge is so-called single electron pump. If we construct quantum dots as shown here, sorry, I have some technical problems. If you have two quantum dots here, and you apply voltage by these probes, you can, using Coulomb blockade, control number of electrons which flow. So you know current, you know frequency which you change this barrier to allow electron hopping, and knowing current, you can determine frequency with which you change these barriers. You can determine again from that you have again access to electron charge. Yeah? And present accuracy is a little lower than quantum Hall effect give and Josephson junction, but still it's very interesting phenomenon. And now what happens? You can have access to this triangle. You have access to this triangle, namely you have single electron transport determination of E, of electron charge, you have also Josephson effect, you have quantum Hall effect, so you have redundancy of phenomena, and also you can measure quantum Hall effect or Josephson effect in many different materials. So the question is, can we use solid-state physics to test now accuracy? And it could be that new physics will make that either from quantum Hall effect or comparing these charges here, we will have some disagreement which will be sign of new physics. So this kind of question which could be asked here in context of this high precision measurements. And now we turn after this methodology application, after this application in search for new physics, we turn to third topic is understanding of quantum Hall effects, and I start from integer quantum Hall effect. And first explanation, or attempt to explain, came very early after discovery, and is due to Thouless. Thouless found that if you want to determine Hall effect, the Hall effect from Hubbard formula, which give us a quantum mechanical prescription how calculate conductivity tensor. So he found that this Rxy can be expressed by this formula, which is again Planck constant elementary charge. And this gamma here is Berry phase for wave function of electrons below Fermi energy. So it's Berry phase of electrons which are sitting here. And if these bands are occupied totally, he demonstrated, he showed this Berry phase is 2 pi times integer number. And he demonstrated this integer number is number of Landau levels. So this big achievement of Thouless and brought his to Nobel Prize, he didn't use a language of Berry phase because Berry, as you know, did his famous paper in 84, not 82. But actually it is exactly what he calculated was Berry phase. And also what he showed that this Hall effect can be expressed by this h over E2, and C is Chern number, and this Chern number is integer, or which is number of levels which are here. So this was first explanation, and this explanation was followed by another one, which is in a sense consistent with that, because probably many of you know, now we know very well, correspondence between in topological system between bulk and boundary. Namely, if system is non-trivial topologically, it must exist boundary states. It's kind of things which maybe look a little artificial, but if you go and take just Schrödinger equation, you arrive to the same conclusion, because if you put together two materials with different for instance, inverted band structure, not inverted band structure, and you look for stitching of the wave function, you very quickly arrive to the conclusion that must be boundary states. Yeah? So topology, of course, does not introduce new physics. If you have proper Hamiltonian and properly calculate everything, you get the same answer. But like group theory, allow us to understand before calculation. And the same situation is here. Before calculation, we know that must exist some boundary states. And these boundary states actually were invented or found also in Halperin was the first who noted that if you have sample now with edges, not infinite sample, but finite sample with edges, just you have edges, of course, linear sample. Electrons cannot escape from your sample, which means that must be, if you point electron states, they must behave like that and give rise to this boundary states, one-dimensional boundary states, which cross Fermi energy. And these boundary states actually carry current. We have this current which we use to calculate resistance, and this current is carrying on, according to this Halperin observation, by these one-dimensional states which are as the edges of the material. And Butiker found that actually, knowing that we have these one-dimensional states, we can calculate group velocity for the state. We can calculate density of states. And if these one-dimensional states are flat, or we have low velocity, but we have high density of states. And if you calculate now current which flows, these two things cancel, and you end up with current which depends only, or resistance, if you divide current, voltage by current, which depends only, again, on Planck constant, charge, and number of Landau levels, which are here below the Fermi energy. And this result is independent of shape of the sample, scattering, and so on, because these states, these one-dimensional states, are chiral. So to go back, electron cannot go back because electron should tunnel. To go back should tunnel through the sample, but sample is macroscopic, it's several hundred micrometers. So electron cannot tunnel from here to here, and therefore this, any electron which entered here is leaving here and not being backscattered. What is also important that in both models of Thouless model, we have to have Fermi energy pinned in the gap between Landau levels. And how it is possible that we have pinning of this gap here? It is possible because there always exists some impurities which pin the Landau level. If you would not have impurities, then Fermi energy will jump if you change gate voltage and change magnetic field from one Landau level to another one. It stays in the gap between Landau levels because you have states. And actually knowing the width of this, plateau, you can very easily calculate, this concentration of impurities is just capacitance of your device and this gate voltage width divided by charge. So we know that impurities must exist, and in this case are very positive, give you very positive effect, allow you to keep Fermi energy between Landau levels. Now we turn from quantum Hall effect toward topological materials. And here you see an old paper done here, which is what happens if you mix up this inverted bandgap semiconductor with standard semiconductors. If you mix up these two materials, at some point you end up with a situation that this gamma 6 band approaches gamma 8 band, and KP interaction means that you end up with Dirac cons. And this probably, this paper is first observation of Dirac cons in condensed matter situation. And characteristic way is that we have constant velocity for such dispersion. And this constant velocity is 300 times smaller than in case of light. And it's very similar to a little accidental in graphene also, or in bismuth compounds, or lead compounds in mercury compounds is a little larger. And you see consequence of the Dirac situation if you have if you plot effective mass as a function of k vector, it's n to minus 1/3, you see that effective mass increases linearly, like for Dirac band, linearly with k vector. So now we have this possibility of topological material in the range which is for concentration below this crossing point. And what is interesting is crossing point and topological range. Let's start from crossing point. And what was found, it was kind of interesting finding, that this material are p-type. What means that there are acceptors in the sample, which can bound holes. And gap, since gap is 0, we do not have gap is 0. As you see here, these acceptor states attached to this heavy Hall valence band must be degenerate with the conduction band. And this degeneracy have several important consequences. First, you can imagine that you have Coulomb interaction, that you have some compensation, and because you have neutral acceptor above and ionized acceptor below Fermi energy, you can imagine which acceptor is ionized, which not, is the one who is near donor, ionized donor would be would be ionized. So you have formation of pairs which compensate actually charge. So you have no too much of scattering. And also, if you think a while, you have different energy if you want to add electron and take out electron. You can imagine that the Coulomb gap would exist, because to add electron, you need more energy to take out electron. So you have Coulomb gap, so you have no resonance scattering between the states here and here, because there is no states as a Fermi energy. And at the end, you have high electron mobility. And in addition, if you have manganese doped sample, you have this magnetic polaron which forms and opens this gap even further. So experimentally, it was found indeed that this mobility is very large. It's 6 million actually in this sample. So we went up to 22 million under pressure. And for years, it was the highest observed mobility in any material. And this is not, it's not error of measurement, because if you measure quantum oscillation, you also see that they start at very, very low magnetic field, about 20 millitesla, which means that mobility must be very high. So it's a kind of situation, three-dimensional case. But what happens if you now make quantum well? If you make now quantum well of this mercury telluride. If you make quantum well of this material, you can calculate where acceptors are sitting, and you found out that acceptors are not the generate energy of acceptor with conduction band, but is whole Dirac band. So we have acceptor now degenerates, these are acceptor states. Here are acceptor states which are not the center of quantum well, and you see that you have acceptor band which is degenerate with valence band. So you have such a situation. So now if you have electrons, there is a lot of ionized acceptors which scatter your electrons. By contrast, if you go with Fermi energy to this whole portion of Dirac cons, you end up with situations that you have resonance state, and again you expect high mobility. So in case of electron, we have high electron mobility in 3D and low Hall mobility, but in 2D we have opposite situation. We have low electron mobility by high Hall mobility. And what the experiment tells, you have here quantum Hall effect, and you see that quantum Hall effect for holes extends to much lower magnetic field. Here's magnetic field. Here's gate voltage by which you can change carrier density. And color code gives you Hall resistance. And you see this Hall resistance much lower magnetic field for holes than for electrons, contrary to other materials. And you can put actually this sample to niobium magnet. You do not need superconducting magnet. And if you change electron density and constant magnetic field given by this niobium constant magnet, you see beautiful plateau, which is in very weak magnetic field in this material. But we said that even better situation should occur if you add manganese. In three-dimensional case, it was very clear, and it's also clear in 2D case. If you take manganese sample, you see that this Hall effect starts even lower magnetic field of the order of 100 millitesla, and this plateau continues till 9 Tesla. Why it continues? Because you have this acceptor state degenerate with your Landau levels, and electrons are taken from this acceptor state to this increasing density of state with the magnetic field, and you have very wide plateau in this material. So you see the role of impurities very clear here. And now we turn to new effect, not quantum Hall effect, but quantum spin Hall effect. And now we speak about two-dimensional system, about quantum well. And we know that we have, of course, in standard system, cation states here, in anion states here, and you have gap between. But if you take now topological system, situation changes, because now you have anion p states above cation p states, and if you look for you had you have this topological invariant which is not zero, and you put with vacuum which has topological invariant zero, you expect boundary states. Yeah? You expect boundary states. Also, you can think about stitching of the wave function, and you will get the same results. But now, since you are in zero magnetic field, the states must be doubly degenerate because, of course, you have a Cramer's theorem which works. So you have two states which are connected by time reversal symmetry operator, and therefore you have helical situation, not chiral situation, but helical situation. Electrons go here in z direction, another electron, as required by time reversal symmetry, is going in opposite direction, and spin of this electron is opposite to spin of that electron. And you expect quantized value in zero magnetic field, which is now h/2, because you have these two helical states on both sides. And what about experiment? What experiment tells? And experiment is shown here. And what you see is that if you have very thin sample of this mercury telluride, you expect trivial gap, that S states pushed by confinement is very high, P states are lower, and you have trivial situation. And nothing special happen. You have infinite resistance if your Fermi energies tuned through the energy gap here. But situation changes here. If you now have topological situation, you have this edge states, and you see that you have non-infinite but finite resistance here, Hall resistance. Unfortunately, what you see here is that this quantization is very poor. You have to take very small sample to have something which was predicted theoretically. If you take longer sample, something is wrong, this quantization does not occur, or is far from. And this is shown here how it looks like at two temperatures, so you cannot say that this plateau as before with accuracy 10 to minus 10. Here accuracy is maybe factor of 2 or something like that. And also if you take gates, finger gates, you end up with the same situations that quantization is not very good actually. So reason, now question is, what is the reason? Why we do not observe this quantization in this case? And the reason are impurities, which I mentioned are very important in quantum Hall effect to keep Fermi energy within the gap. But here, although they are important, that they keep Fermi energy within gap. You can scan the gap because you have this impurity which spins the Fermi energy. But now what also this impurity gives, this impurity have a non-zero spin, and therefore there is possible scattering between these two spin states. Yeah? This impurity carry a spin, and it could be spin exchange between this electron and this helical state here, electron helical state here, impurity reverse spin, and spin is kind of conserved. So this kind of model which we propose to understand this weak degree of quantization in this case. And actually to calculate that quantitatively, you have to calculate exchange coupling between these edge electrons and this acceptor states. You have to calculate Kondo effect because actually this exchange coupling is very large because this exchange coupling is inversely proportional to square of energy difference between these holes and electron and boundary states at the Fermi energy. This is a few millieV. So this coupling between electrons and holes is very large. And this gives rise to Kondo effect. And Kondo effect, if you have Kondo effect, it means that this acceptor, which has a spin, can attract the cloud of electrons from this edge states and form a bound state. And this gives rise to very strong scattering, actually. This gives rise to scattering which has so-called unitary limit. And then you have to take into account spin-orbit interactions, that you have anisotropic, this exchange coupling. You have to take into account interaction, because in one-dimensional case, interaction between electrons are very large. And then you can calculate this backscattering rate. So you can calculate what is per second, how many event of this transition between this state to that state can occur. And doing all that, you end up with here theory with no adjustable parameter. Here you have calculation for few value of distance between electron edge states and hole on acceptors. It depends a little bit, but not too much. And you see that for 1 micron sample, you expect value which is close to quantization, as expected here. But if you take larger value, as here, you get much larger resistance, yeah, because backscattering occurs, and transmission coefficient for this one-dimensional transport is not 1, because electrons scatter back, and this reduces current and gives higher resistance. So this kind of understanding of quantum spin Hall effect, that due to proximity of this helical states and presence of impurities, there is no topological protection, or very weak topological protection. But again, we come back to doping with magnetic impurities. This was mercury telluride without magnetic impurities. What happens if you now add to material, to mercury telluride, these magnetic impurities? As we mentioned, there is bound magnetic polaron formation, and some of you may know that if your spin is split by external magnetic field or exchange interaction, this Kondo effect is very strongly reduced. Kondo effect is not any more efficient. And what happens in a manganese sample, that if you measure conductance this time, not resistances from here, you have poor quantization, low conductance. Conductance should be 2 and is much lower. But if you lower temperature now, you start to recover this quantized value more or less. And this is due to, we believe, due to that you kill Kondo effect, which is very important, to kill this topological protection in sample without manganese. And now we turn to another quantum. Quantum effect, is quantum anomalous Hall effect. Now we ask the question, what happens if we have quantum well, like that, where time reversal symmetry is conserved, and we add a lot of magnetic impurities that we produce huge splitting of this conduction band and of the valence band, which are inverted. Yeah, here it's p-type, it's anion, and here are cations. So if you cleverly do that, if you put appropriate impurities and appropriate number of these impurities, you end up with a very interesting situation, that you have inverted situation in one spin channel, but not inverted situation in other spin channel. So you have bondary states, which now only can carry one spin direction, because only topological situation occurs for one spin channel. And you expect, therefore, chiral state, yeah, not helical states. Time reversal symmetry is broken by the presence of non-zero magnetization, and Kramer's theory is not present. You should expect something like that. And beautiful experiments done in Beijing shows that indeed macroscopic samples now, they use knife to produce this Hall bridge. At some concentration of carriers, which you regulate again by gate, you have quantization, very nice quantization, corresponding to 1, because now you have one chiral channel. And this resistance, the longitudinal resistance, tries to go to 0. So this quantum anomalous Hall effect produces 0 magnetic field, non-zero magnetization, but 0 magnetic field, produces very nice quantized value. And people started to make resistance standard of that. Here's measurements for in 10 Tesla for standard device, quantum Hall effect. And if you measure 50 times, you have this kind of scattering between data. Here you have to measure for quantum anomalous Hall effect. You have to be in much lower temperature. You are in small magnetic field just to rid of domains, but it's kind of unimportant. But you see that accuracy is maybe 1 order or 2 orders of magnitude lower, but still it is impressive. You have accuracy of the order of 10 to minus 8. Yeah? So this kind of very impressive. We expect progress to make this very precise. Only problem is this very low temperature. And also that if you put high current, you have also decrease of this precision of quantization. This data change. If you put higher instead of plateau, you get to another value. So we should work hard to get access to higher temperature and higher currents. And what is the reason that we need low temperature and we need low currents? The reason is that there are impurities. Again, there are impurities between this conduction band and valence band, and this impurity gives rise to additional, by hopping conductivity, additional parallel conductance and kill quantization precision, except if you are very low current at very low temperature. And now, maybe you can find material with better concentration of impurities, which pins the Fermi energy but give less scattering. And we have made calculation for chromium doped mercury telluride. And we found that interaction between spin is, in many cases, ferromagnetic, which is good. We need spins to be organized in zero magnetic field. Here is spin coupling as a function of distance between spins. Red mean ferromagnetic interaction, blue anti-ferromagnetic interaction. And we also calculated what happens if spins, chromium spins, are polarized. And we found that for certain orientation of magnetization, we have a gap, which is, and this corresponds to situation, that in one channel you have inverted situation and in another channel not inverted situation. We also calculated Berry curvature and found that Berry phase or Chern number is 0, so we expect this quantized value. So this brings me to conclusions. Chart dopants increase plateau width, which is good, but diminish quantization precision by backscattering between helical channels in quantum spin Hall effect. And also, these impurities produce parallel hopping conductivity in quantum anomalous Hall effect. Magnetic dopants improve quantum Hall effect and quantum spin Hall effect. In this case, is by killing Kondo effect. And magnetic dopants are crucial for quantum anomalous Hall effect. Due to magnetic dopants, we have quantum anomalous Hall effect. Another outlook, mercury telluride are good material. Particularly quantum Hall effect should be expected in very weak magnetic field in quantum manganese telluride. And in chromium samples, we expect quantum anomalous Hall effect. And such MB to produce such material, it's available in Duisburg, it's available in Rzeszów. And the very results from Rzeszów for quantum Hall effect in quantum wells of mercury telluride were obtained just 2 weeks ago or something like that. So this kind of very recent results. Thank you very much for your attention.
Thank you for this talk, for the survey of quantum Hall effects. So now we have time for questions. And who would like to start? There was a lot of material, but I see the question from IFPAD.
Just can you comment more on the last result from Rzeszów? What is? So I didn't see what is the quantity that is quantized. So what are the steps? So
what they measure, it's Hall resistance. They measure Hall resistance as a function of magnetic field in quantum well of mercury telluride. And they see nice quantization. Yeah, so it's standard quantum Hall effect.
Standard quantum. Okay, thank you.
And samples are macroscopic, a few millimeters. So we do not expect quantum spin Hall effect. Resistance of channels will be very large, yeah, because samples macroscopic. And of course, this is not as interesting. What we look for, samples with manganese or chromium, which should show very good quantum Hall effect in case of manganese and very good quantum anomalous Hall effect in case of chromium.
Thank you. Actually, I have a question, but from a very different discipline, because I'm representing the cold atom community, and in my community, it's very popular to speak that we can use optical lattices to model different Hamiltonians and then use them to other disciplines like condensed matter, or also to simulate Dirac cones and topological materials. What's your opinion about it?
Yeah, it's fascinating. Of course, we wait, as you know, not only for quantum Hall effect and this optical lattices. People work for superconductivity in Hubbard model, and there are many expectations. What is probably interesting to note is that if you go to material parameters, these two systems are complementary. Usually they are not exactly in the same parameter space. Yeah? And this make maybe a situation very interesting, that we have access to parameter space which is not possible to be attended in the case of condensed matter materials, and vice versa. But of course, it's fantastic what can be done with optical lattices.
So well, actually, I see that very often we have very clean materials in optical lattices, but not much is spoken about dopants or about impurities, which apparently are the crucial, actually.
Mm-hmm. Yeah, so there is very interesting that in this particular case you need not too many, but not too much, not too little impurities to observe these effects. Yeah, in this case, and probably in optical lattices also very interesting. Do you have problem with impurities? How it is?
There's no impurities.
Nobody speaks. Nobody believes that there are.
No. There are, of course. There is research, also experimental one, about putting some impurities in optical lattices, or other kind of atom, or atom in a different level, but it's not the main trend, I would say. It's probably not taken seriously enough, I would say. Okay, other questions? We have still some time. I have also, let's see the question there from Oliver. Good.
Hi, I guess, because this is not my field at all, I guess the thing that I was most interested in from your talk was this idea that experiments along these lines could tell us something about like beyond standard model physics, like about dark matter or something. So could you comment on like how difficult, how far away it would be, how expensive it would be to say start ruling out something about dark matter using experiments along this line?
Sorry, I didn't catch. I should stop and say.
So you mentioned that there was some possibility of like excluding some dark matter candidates or something using experiments, so very high precision experiments on these lines.
Yeah.
Could you elaborate on that a bit and say like?
So, so what I can say more, for sure, if you take to this equation I mentioned, it's of course dedicate what we understand by experimental energy scale. If we understand by energy scale millikelvin temperature, that we do everything in millikelvin temperature, and if we assume that energy scale needed is 10 to 15 EV, for instance, it's kind of scale. So you see that you have to get precision 10 to minus 18 instead of 10 to minus 10. So of course it looks challenging, but of course people, experimentators make always big progress. So probably we have to work very hard still on precision, both in optics and in solid state, and look how far we can go. Yeah? And in optics, as you know, it's very interesting that nowadays you have to take into account, for instance, nucleus structure. Yeah? You have to take quark into account and so on. You have to take really a lot to get precision, to get experiment to agree with theory. This advantage, but disadvantage also, that you have to very deeply work on very many things. Maybe in quantum Hall effects, you have this number 1, and a deviation from this number 1 could be a sign that some additional interaction happens. But of course, maybe this topological prediction is resistant to everything. But one can naively say that like impurities change something, you can imagine also that having new energy scale entering this system, this precision will be broken. Yeah.
Also very happy about the results from Rzeszów. So do you collaborate with Rzeszów?
Yeah. So Tomek Wojtowicz is responsible for helping them. Actually, they have also part of equipment taken from us, from Wojtek Knapp from Centrum, and there is kind of both MagTop and etc. work very hard to make this system working well, and these first results are very encouraging. Yeah. So it's kind of a very close collaboration with them.
So they built a lot of labs actually in Rzeszów recently, also in quantum optics. If you do not have more questions, then I propose to thank the speaker again.